Hi everybody, in this lecture we are going to be going over part of our global change unit that covers ozone depletion and also the climate crisis. You can find this information in section 18.7 on the ozone depletion and then chapter 19 on climate change from living in the environment. Just a reminder, when we talk about ozone, we're looking at stratospheric ozone in this case, not surface level or tropospheric ozone. So remember where we are talking about when we talked about the reaction that creates ozone, how it protects us from UV radiation, and where CFCs are found and how they actually deplete that ozone layer. So recall that the layer of the ozone in the stratosphere protects our surface from harmful UV radiation. It doesn't filter out all UV radiation, but it is able to filter out enough that we can survive at the surface and we have, less chance of mutations in our DNA and damage to surfaces as associated with incoming UV. Since the mid-1900s, data reveals that we've seen a loss of ozone molecules. This is particularly bad at the poles. Antarctica is seeing a higher rate of ozone loss than the Arctic. And we also see that this is associated with seasonal change, and I'll talk about that in just a second. Ooh, bless you. So the thinning correlates with the first use of ozone-depleting chemicals. ODCs. So ODCs include things like CFCs. We find CFCs in insulation materials, Freon in air conditioning and refrigerators, and they used to be used in aerosol materials. We also see CFCs in solvents, cleaners, insulation, etc. There's other ozone-depleting chemicals out there, halons, and which you see in certain light bulbs. Other chlorine-containing materials are going to be basically responsible for depleting ozone materials. We've seen that ozone is being, significantly reduced since these materials came into use in the 1950s. And we typically refer to the amount of ozone in a unit called Dobson units. And so the lower the Dobson unit, the less ozone we see in our atmosphere. The hole, which is really not a hole, but rather a thinning of the layer that we're talking about, forms in Antarctica. And we tend to see it more in the fall months or the early winter months. And the opposite time of year, you would see a similar thinning of atmospheric material, ozone, in the Arctic. The reason for this is that a polar vortex, which is a circular wind pattern around the poles, isolates a pocket of air over those regions during either the winter months in the Antarctic or the summer months in the Arctic. And when the sun returns, the ice crystals, which collect ozone-depleting materials, melt. And so we tend to see that this will destroy ozone. And you can see the reactions here where you have a chloride material, which reacts to free up chlorine. That is going to react with ozone in the atmosphere to create ClO and O2, which is oxygen. And then that material can break down and basically retain the chlorine, which can then go back into this reaction as well as creating O2. But that's not what we want, right? We want ozone to be available to us. And the problem with this is that if you have less and less ozone, if your Dobson units are going down, you're going to increase the amount of UV radiation that actually reaches the surface. This can lead to greater chance of carcinomas, melanomas, and other skin cancers. This can lead to greater chance for cataracts. This can lead to easier sunburning of skin. This can lead to UV radiation that breaks down man-made materials. There's a lot of problems associated with it. So in the mid-1980s, research was done that basically quantified the amount of ozone in Dobson units, measured the size of the area of thinning of the ozone layer, and correlated all that information with the amount of CFCs in our atmosphere. And this was a really trying time for the planet, but the data was really sort of unopposed. There was really no question that this was happening. So CFC usage was cut by a global movement called the Montreal Protocol, which was passed in 1987. And since then, we have seriously reduced the amount of CFCs that we use. Other ODCs are still in use. Halons, like I talked about, being found in some light bulbs, HBFCs, methyl bromide, hydrogen chloride, etc. These are still things that contain chlorine and can cause similar issues, but they're not as used in sort of as much volume as we saw CFCs. So we have seen basically that there's a pretty longevity of ozone depleting chemicals in the atmosphere. It's taking a while for that material to break down and be no longer present. It will eventually precipitate down, but it's so high in the atmosphere that that's hard for it to happen. But we've been able to curb the effects, and we are seeing the layer of thinning in the ozone start to come back. It's a slow process, but it is happening. And so we are no longer at quite as high risk for human health effects like skin cancer, for effects on plants and animals, and for effects on man-made materials like plastics, paints, etc. So this is a really positive example of how global change can be overcome by a global movement where everyone agrees with the science and agrees to make a large change to curb the effects of whatever the human impact was on the environment in order to protect human life, in order to protect wildlife, and in order to protect our way of life on this planet. Changes in Earth's climate, however, is what we're experiencing right now. And all of this is going to be happening in the troposphere, right? So that lower level of the atmosphere. Recall from Unit 3, I think, that climate is determined by average weather over a 30-year period. But we use things like paleoclimate data collected through a variety of means to be able to examine how Earth's climate has changed over the last, let's say, millions of years. In the data that we're going to look at here, we're going to look at 1 million years, but we've got data that goes back farther, paleoclimate data that can basically retrodict what the planet looked like and what types of climates we saw on the planet based on evidence that we find. The global climate has gone through periods of global cooling, which we call glacial periods, and global warming, which we call interglacial periods, and we basically can track those patterns very easily. Most recently, we've come out of the last mini ice age, about 10,000 years ago, correlated with the establishment of agriculture and the rise of, large human civilizations. But if we were to sort of narrow down our time scale that we're looking at, the climate change patterns that we're observing have happened, over the last 200 years. And we're starting to see major shifts beyond what we would have seen naturally. So how do we know what the temperatures were in the past? A lot of people ask this question. Most of our data is collected from isotopes in rock samples, in ocean sediment samples, in fossilized samples. We do an incredible amount of work examining air pockets trapped in ice cores to determine what past atmospheric composition looked like. We can observe tree rings that indicate climate patterns by sort of the, greater periods of growth may be associated with warmer, wetter periods versus slower periods of growth may be associated with cooler and drier periods. But we want to know, okay, what was the tropospheric chemical composition in Earth's past climates? And that's going to give us an indication of greenhouse gas concentrations. We can determine temperature trends from that. And you can even see event scale things like solar irradiance, snowfall, and fire activity when you look at these ice cores. So samples indicate that primary greenhouse gases are found in our atmosphere, water vapor, carbon dioxide, etc., and that there's a strong correlation between the fluctuation of greenhouse gases, such as CO2, and temperature patterns in our climate. And if you were to, observe the data, you can see a strong correlation between changes in CO2 concentration and temperature patterns. And there's some cyclical nature to this. We see some regularity in these periods, and we'll talk about what causes that in just a moment. But essentially, the ice cores have shown that CO2 levels in the troposphere now are the highest that they've been in, this is an outdated value. They're now the highest they've been in about, I think last value I looked at was 15 million years. So essentially we're seeing a major change, and we need to sort of track where this goes. Today we are looking at a CO2 concentration of 418 parts per million. And the highest concentrations that we've seen in the past are somewhere around 300 parts per million. So we're totally off the record at this point, and we'll sort of see how that correlates to temperature. We know that climate is affected by natural forces, but anthropogenic factors cannot be denied. So there's a natural greenhouse gas effect that allows our surface temperature to remain high, comparatively to if we didn't have an atmosphere with all these greenhouse gases. It would fluctuate between really hot in the sunlight and really cold without it. But the natural greenhouse gas values are being affected by anthropogenic factors. So we see emissions from CO2, we see emissions from methane, we see emissions from N2O. Also, human activities are releasing waste heat into the atmosphere and other types of air pollution that may be affecting climate change. We have to consider the level of solar input, so how much electromagnetic irradiance is the sun actually emitting from time to time. That fluctuates depending on cycles in the sun. We don't right now have any evidence that that is affecting climate change at this point in time, although it has in the past. In fact, solar input, or solar output I should say, is actually down from recent years, so that's something to think about. The reflectivity of surfaces, called an albedo, such as ice or snow or areas of the desert, how much sunlight is actually irradiated back out into space or reflected back out into space, can affect our climates. Obviously, the oceans play a huge role. They are a huge heat sink. They are a huge CO2 sink, and they're really a climate moderator. And the level of cloud cover. Clouds can act as a blanket and hold heat closer to the surface, but they can also act as a shield and actually irradiate or absorb or reflect sun back out into the atmosphere. The IPCC, which is the International Panel on Climate Change, is an organization that you should really know. It was organized in 1988, so, a year after the Montreal Protocol was passed and started to work, the IPCC came to be, and climate scientists started talking about, okay, what are these other major global change issues that we should be thinking about? And they've basically come out and stated over the last, 30 plus years that Earth's lower atmosphere is warming due to the increased greenhouse gas emissions from human activities. We have seen temperatures rise by about 1.5 degrees Fahrenheit as of today. And we have seen CO2 emissions rise, around 80% between the 70s and today. These changes are drastically altering Earth's climate, causing rapid ecological, economic, and social disruption due to a number of problems. And so IPCC said this, and they continue to say this when they meet every few years. In this image, we see sort of ways in which heat is being added to the troposphere, and ways in which it might be being taken out of the troposphere. And we're seeing that, human impacts are forcing more global warming factors than they are forcing more global cooling factors. CO2 and methane and nitrous oxide are the things that we want to pay particular attention to when we're putting out greenhouse gases. We produce other greenhouse gases like ozone, and CFCs even can be a greenhouse gas, but these are the big three that you should be aware of. Water vapor is sort of the fourth biggest one to be concerned about, but we have less of an impact on changing water vapor directly. We are shifting the amount of water vapor in the atmosphere indirectly, but mostly due to the warming effect from these other gases. Natural climate forces are going to be shifting Earth's climate on a fairly regular interval. We talked about seeing that sort of cyclical pattern of climate change between glacial and interglacial periods over the last million years or so. And this is because of three main factors. Eccentricity, which is the elliptical nature of Earth's orbit. Is it a circle that goes around the sun evenly, or do we have periods where we're farther from the sun than we are closer to it? So eccentricity is basically the shape of Earth's orbit around the sun, and going to determine how close we are to the sun and how much solar irradiance we're actually getting at Earth's surface. The obliquity of Earth's axial tilt is going to basically shift how tilted we are as a planet. So we know that Earth is not straight up and down and just spins around a pole that's straight, but rather we are tilted in our axis. And so when we have a greater axial tilt, or we have a slightly different axial tilt, that's going to shift how much the solar input is at any one point on Earth's surface, and that can basically cause more or less solar irradiance to reach the surface and have an effect. And then where our Earth is pointing, sort of where the North Pole actually points, shifts as well. So even though we may be a little like this on our obliquity, precession is the wobble of that actual direction. Right now, our pole is pointing closest to the North Star, but over the period of about 22,000 years, I'll say, we shift, and the other star that we shift towards is Vega. So precession is the direction that tilt is actually going in. And that too can change the amount of radiation emitted or absorbed at Earth's surface. And so we see regular periods of glacial and interglacial change at fairly regular intervals when all of these things align. Where, we have a particularly hot interglacial period and a particularly cold glacial period, and we move in and out of these periods over, the course of thousands of years. Unfortunately, Milankovitch cycles do not predict or do not determine what we're experiencing right now. Albedo, as I said, is the reflectivity power of a particular surface. The more reflectivity, the less solar irradiance. So when we're in a very strong glacial period, we reflect more of the solar irradiance than we absorb it. And when we're in a particularly strong interglacial period, we absorb more of that solar irradiance than we reflect it. And this can lead to positive feedback cycle, which can essentially force or move an entire system one direction or the other, depending on the level of albedo from Earth's surface. Right now, because we are seeing snow melt and glacial ice melt, we are losing albedo, which means we're increasing the amount of solar irradiance that we absorb at Earth's surface, and that's causing more heating of Earth's surface. As I said, oceans regulate climate. They absorb CO2 from the atmosphere, which can lead to things like ocean acidification. Right now, we think they're absorbing about 30% of our anthropogenic outputs of CO2. Ocean temperatures are rising, so the heat in the atmosphere is also being absorbed by the ocean. It's a huge heat sink. And oceans can be somewhat reflective, so some sunlight is going to be reflected back out into space off of our oceans. So oceans play a huge regulatory role in our climate on our planet. Clouds, as I said, can have both a warming and cooling effect. If we reflect solar radiance back out into space from our clouds, then we tend to be cooling, and we see this with brown smog clouds and their ability to actually cool the surface where we see those clouds. Since we've cleaned up a lot of our visible air pollution, we no longer see as much of a cooling effect from our atmospheric cloud cover. And some clouds can actually act as a warming blanket. If they're sort of covering the surface, they can trap heat in the lower atmosphere temporarily as well. So clouds kind of play a dual role in climate. And we've seen that, like I said, air pollution can slow global warming when we have lots of particulates in the atmosphere that are blocking sunlight from coming in. But the more we clean the air and the less visible air pollution there is, the less effect that's having. So if you were to examine only natural forcings, we don't explain the rate of change that we're seeing right now. If you observe only anthropogenic forcings, we also don't fully explain the rate of change that we're seeing right now. And so we need to tie together both natural forcings and anthropogenic forcings to really understand the modeling that we're observing here on the planet. And this is a slightly older data set, but it's important to realize that the cause of climate change, is more anthropogenic than it is natural. Effects can range. We have severe drought in some areas. We have severe weather events in some areas, more extreme monsoons in some areas. We're certainly seeing glacial ice melt, ice cap melt, and alpine glacier melt. We are observing permafrost melt in the Arctic regions. Sea level is rising because of that extra water that is now melted and run off into our oceans. We're seeing major threats to biodiversity, especially when it comes to habitat ranges for certain organisms, which leaves regions more vulnerable to invasive species. We're worried that we're going to start to see greater declines in agriculture due to things like desertification in certain areas. And certainly that's going to lead to human health threats like the higher prevalence of disease and ocean acidification, which is the factors involved with more CO2 in our oceans causing an acidification event. And I'll talk about that in just a second. So any of these that are positive feedbacks are going to amplify the environmental change. Things like permafrost melt, glacial ice melt, etc. are all going to be part of positive feedback. Some of our natural negative feedback systems are currently being disrupted. And that is, another force that's pushing climate change further and further away from our normal climate factors. There's lots of impacts that we could talk about. There's a really nice infographic that kind of covers some of that and talks about, okay, right now we're predicting up to 3 degrees C change. We're starting to see environmental refugees being everywhere. We're starting to see food shortages. We're starting to see our ice caps melt, and we're starting to see organisms go extinct. These things are happening for sure. These things are starting to happen, and these things are starting to happen as well. How far we go with this, or what is the permanent outcome for this, we don't know yet, simply because we don't have the right modeling for it, and we don't exactly know what's going to happen with the human activities. We are seeing glacial minimums becoming less and less, and glacial maximums becoming less and less. We are seeing sea level rise, and these are issues that are very visible in the data and certainly can't be denied by what we see. Ocean acidification is sort of the silent partner here, where the other carbon dioxide problem is that as the oceans absorb more atmospheric CO2, that CO2 enters into the water, reacts with water, and forms a carbonic acid. A carbonic acid is going to further go through a chemical process by which the material actually ionizes so that we end up with hydrogen ions, which we know are a measure of pH, and bicarbonate ions. And the lower the pH in the water, the more difficult it is for organisms. One of the biggest problems is calcium carbonate containing materials, which are the building blocks and sort of the shells or skeletal structures of many marine organisms, can't form as easily, or we tend to see deformations or deformations associated with the larval stages of these organisms when they're trying to develop. So there's a pretty strong correlation between atmospheric CO2 rising, seawater CO2 rising, and seawater pH lowering. So, these things are pretty strongly correlated, and this is definitely a big issue. We are seeing effects mostly on calcifying species right now: oysters, clams, urchins, corals, plankton, etc. And, when you look at the actual, let's say, forams that are forming, or larval organisms that are trying to form into adult stages, we tend to see them having difficulty forming these tests or these shells, and that's certainly problematic for those species. If sea pH continues to decline, other species will also be affected in their ability to buffer their internal conditions. And so even non-calcifying organisms can start to be affected when the pH shifts too dramatically. So we really need to start paying attention to this particular factor and hope that some of that CO2 can really enter into the deep ocean storage where we want it to go. So our most pressing solution is obviously to reduce greenhouse gas emissions, collect and remove those emissions from the atmosphere via carbon sequestration projects, geoengineer our planet to increase albedo or to decrease the effects of climate change in some way. This is going to involve changing the role of government and policies that are put out by world governments, and changing the role that corporations play in their interaction with the atmosphere, not just the consumer and the person using products, but the corporations that are actually, allowing these gas emissions to come from their products and their services. And we can try and lessen the impacts as much as we want, but we are going to see these impacts. So we also have to start coming up with strategies to prepare for climate disruption. That can include moving entire communities away from the coast. That can include getting ready for major weather events. That can include preparing for industries being disrupted by things like ocean acidification, such as the shellfishing industry, etc. So we need to start putting in responses to climate changing effects that make sense in the long term. Carbon sequestration is probably the project right now that's of most interest, because if we can remove CO2 and sequester it somewhere or use that CO2 somehow, we're going to reduce the effects that we're seeing. And so we've talked about ways in which we can clean our air, and those tend to focus on non-CO2 emissions, non-methane emissions, but these technologies can be improved or changed to also remove CO2 emissions as well. Projects like the Clean Air Act, the Clean Skies Initiative, etc., are, working towards trying to limit air pollution. There was hope on the global scale that we could enact a policy much like the Montreal Protocol. When the Kyoto Protocol was written, there was an agreement by some nations to cut greenhouse gas emissions. Unfortunately, major players did not ratify the Kyoto Protocol, including the United States, and that left it essentially not very effective, and certainly nowhere near as effective as the Montreal Protocol. The most recent sort of global agreement has been the Paris Agreement in 2015, but the US has oscillated whether or not we ratified the Paris Agreement over the last 5 years. So it's difficult to know exactly if there will be a real global push on this, most countries are making individual pushes. We're seeing companies that have pledged to reduce their emissions. We're seeing consumers forcing companies to abide by these concepts and ideas and values. Things like cap and trade programs are going on right now to basically set one total allowance for the amount of emissions and allowing companies between themselves to decide who is going to emit more and who is going to emit less based on who has access to certain technologies. Taxes on emissions, taxes on energy use, subsidies and tax breaks for people who are saving energy, and policies to eliminate fossil fuels and subsidies for fossil fuels are now going into place. California recently made a commitment to stop oil drilling, essentially, by I think it was 2024 or 2034. And hopefully those pushes will start to really get the ball rolling and we'll see a lot more change coming down the line. So, there are things that we can do. There are things that you can do. There are things that we can hold companies and corporations and the government accountable for to try and mitigate and stop the effects of climate change.